So here is my notes of how embedding models work. So we know that embedding model converts words or tokens into vectors of numbers. Like if we have a set of words, I mean is the sentence. What this embedding is, it is split into to the to the word by words, like tokens, and each tokens, like for example this king, um, convert becomes having a vector values. So this vector called an embedding. So the goal is of the embedding is words with similar meaning or usage should ends up near each other into vector space. Like um, what is the semantic um, um, nearby words of the king, like queen, um, um, or any other related words that associated with the king. So if thus um, they would have the same values into their vectors, and what this means is this is dimension or features. So embeddings are coordinates in semantic space. Instead of representing words as labels, like king is category number 5, we will represent them as the coordinates. So this king or this word value, this word um, consists of these values. So they they coordinate systematically to produce this king. Like for example the analogy of the color. So the color purple is equivalent to the combination of RGB or different value of R, green and blue. So each word becomes a point in high dimensional space, and this is called as a vector space or semantic space, embedding space. And let's continue space. Embeddings exist in continuous space. Like here, there is a continuous space. We can see them in the such space or vector space. So meaning the values are flexibles and real numbers. So they are continuous numbers instead of fixed categories. So this allows smooth semantic relationships, like for example puppy, dog, wolf, predator. These words are related to each other. They are semantic relationships, meaning when it comes to this course value, they would have vector values nearly the same to each other. So why similar words become nearby? Like for example, we have the set of words like the model reads, the king ruled the kingdom and the queen ruled the kingdom. So the model notices this part of the sentence. The sentence came from the other data that we gather. Like for example, in the sentence of the books, like that. So the model notices king appears near kingdom, queen appears near kingdom, king and queen behave similarly. So the vector gradually become closer. Example, before the training, we have the random values of this vector from the king and the queen. So they are not relatively connected to each other because of their scores. And after many updates of the model, the model sees that king and queen appears so much in nearby words. Like for example here, king with the kingdom, and they have the similar nearby words. The king has this one ruled, and the queen, they have the similar to the nearby word. So what the models does is it keeps updating um, until the prediction value is correct. Like for example, if you trying to predict king and we expect its values um, of queen, um, it will update it and update again and again until we have um, the less error. And if if the model sees that to the point that it, it that it doesn't have any mistakes, so less errors, then it will stop. Now they point similarly, occupy nearby regions, have similar semantic behavior. So they are similar semantic, meaning um, they are nearby or nearby regions to each other. Next is model starts randomly. At the beginning, king, queen, banana have these random values. The vectors mean nothing yet. Training gradually organizes them until they form the regions, they cluster to each other, like in this photo. Like for example, the king and queen associated to each other because they often appear in many datasets or sentences nearby to each other. Somewhat in this region, they are clustered together. But the banana word, they didn't appear so much in the nearby word in the sentence to each other. That's why they didn't have similar values. So they might appear far away from the region of the king and queen where they belong. Um, Next is context window. What is context window? Embedding models learn from nearby words. Suppose a sentence, the king ruled the kingdom. With a context window of 2, like if we target the king and with a context window of 2, then the nearby context words with a window of 2 will become the and ruled because we step closer. Rolled 1, 2, 1 and 1, 2, 1, 2, like that. Example, training pairs automatically generated. During the training pairs is automatically generated than manual because text is a huge amount of data that we gathered. So manually doing it, it's so much having a painful task. Yeah, that's why during the training, when we gather the sentence or the text that fed into the model, it automatically generated the nearby words, like here in, like for example, if we had a window of 2, so it will be pair like king will this one and the king will be pair this one. And if you had a window of 3, like 1, 2, 3, it will be generated as 1, like that. So the data generates supervision automatically, and those pair of words will be used in the training. Like this is the input, and the model is expected to target the output like this one. If we have input of king and this word king, the expected output target value is the red. And if not so, it will have large amount of loss. And during training, those loss is will become less and less until we have the correct predicted value. Why it called self-supervised learning? Because no human manually labels, like we label king to queen nearby like this one, the pair words. Instead, the text itself generates inputs and targets from nearby words. This is why embedding training is called self-supervised learning. Again, it is called self-supervised learning because the the models automatically um, pair the words, nearby words, to each other. Next is prediction objective. The model learns by predicting nearby words. Uh, like for example, if we have input king, the word king, the expected nearby words may include queen, throne, king, crown, and rule, because um, these words are often appear in many data sets along with the king word. So the model predicts probabilities. Like for example, if we have the word queen, and um, it would have a high predicted probability than banana, because um, the word banana would not appear so much in associated with this word. So good prediction produce low loss. Next is loss functions. Like in the previous videos that we have, the loss function is calculated um, like comparing the predicted value versus the true values. So the difference between the correct value and the other value. The model compares predicted words, expected context words, then compute error. So high error, high loss. Like for example, king. If we have the input of the word king and it predicts banana, then it would produce high error, because these two words is not associated in each other in different sentences or words. They are not. We couldn't see they used together in the same sentence or context. That's why it will produce high error. While the in many contexts or sentences, we often see the king and queen is associated with each other. I use them in many sentences in every different data that we gathered. So the goal is to minimize a prediction error, and these words king and queen are often belong to each other, and during the training they are for sure automatically paired to each other. The input is king and it might produce the queen, because in these sentences or contexts they appear together. Next is gradient descent. So gradient descent is used in the training. Actually, we have the gradient descent algorithm where the parameters is we're going it's part of the training process where we update the parameters towards the minimum loss. I mean, if we achieve that minima, then at that point the model is predicting the right value. So the formula of it, I think, is the parameter subtracted by the gradient of loss with respect to the parameter multiplied by the learning rate. So when the predictions are poor, loss become large, gradients becomes large, vectors move more. When predictions improve, loss becomes smaller, gradients become tiny, vectors become stabilized. Training repeatedly predicts, compute loss, adjust vectors, repeats millions and billions of times until the vectors place where it should be. So what is the dot product? So the dot product measures vector alignment. This is a formula is if we multiply the matrices like this one, and it is the same as this formula. So let's say we have this vector of the king and this vector for the king. So they are using the dot product, 2 times 2 plus 3 times 2 to the 10. So large positive score means similar direction, semantic compatibility, while the negative scores means weak relation, unrelated meanings. So the positive one is they are similar direction, while the negative one are small scores, they are weak relations or unrelated meanings. So it's this is what is cosine similarity? This almost the same as that product we use in these embeddings. Cosine similarity normalizes the vector length. It focuses on direction, semantic similarity rather than raw magnitude. This is commonly used for semantic search, similarity comparison, recommendation systems. So this cosine similarity means gathering their semantic meanings. Like if we have the cosine value of 1, then the words or the vectors might be the same, and if we have the 0 values, they no meaning, they are not unrelated. And if we have the negative values, um, they are opposite to each other. Why similar words are not identical? Why similar words are not identical or will not be the same at all in terms of vectors? Example, king and queen, they are related but not identical or the same values of the vectors because they share properties like royalty, leadership, human. Different properties is masculine, feminine. So vectors become close but that distinguishable because those words are in the vector space are sharing different properties. Yeah. And during the training, um, their vector values would stop if the model predicts the correct one. I mean, if the model is doing well by predicting the correct values, and their vector values would stop at that moment, and they would have not the same but close each other because they are related but not identical. Next is distributed representation. In modern embeddings, meaning is not stored in one dimension. Instead, concepts are distributed across many dimensions. Like for example, royalty may involve in dimension 3, in dimension 17, in dimension 44, in dimension 81, working together. This is called distributed representation, and in fact, because they are in the vector space, they would correlated to each other, but in a sometimes small portion, sometimes it's large amount, right? By the way, we can call the vector values and each of these values as a dimension, like dimension 1, dimension 2, and so on and so forth. And what is dimension versus clusters? Important distinction. Dimensions are axes or features. Example, dimension 1, dimension 2, and dimension. Even though it's so hard to visualize this huge amount of dimensions by our own eyes, we use or shrink it into the two-dimensional representation, so we could use and plot it using this, like this one. And this is called the dimensions in a vector space, like that. This is the direction of Germany. This is the dimension of a direction of Italy, and yeah, this is a 3-dimension that represent the words into this vector space 3-dimension. And clusters are groups of nearby words. So, like this one. If the words and nearby words are often appear to each other and they're semantically or contextually similar, they would appear in the nearby regions or same regions. Example, royalty cluster, king, queen, emperor, and prince might be here or here. They are nearby to each other or the same region. Clusters emerge because vectors become geometrically similar. So what is latent features? During training, dimensions may gradually correlate with hidden semantic patterns. Like for examples, dimension 17 is royalty-like patterns, while the dimension 42 is gender-like patterns. Dimension 63 is emotion-related patterns, like that. So these are called latent features. Like this one, for example, this one, let's say this one and this one might have the meaning, the dimension 1, this dimension 2 meaning. Like, yeah, some of the dimension 17 in the word king, for example, their dimension 17 will be hide in the other word. Like for example, the dimension 17 of the king and the dimension 17 of the banana will not totally the same or far away from each other, because dimension 17 is rotor-like pattern. So we expect that king, or the word king, is more likely high value scores than the banana, because they are natural like patterns. But the king and queen would have the same huge amount of or high values of the dimension 17, because they are like patterns, but they are not actually the same like that. So what's embedding geometry? Embeddings are fundamentally geometric, meaning emerges from distance, angle, direction, neighborhoods, regions in space. Like for example, king minus man plus woman is queen. This works because semantic relationships become geometric directions. Like for example of this, it's called embedding geometry because we could actually subtract it, because they have the distance, the angle, and the neighborhood regions and the space. Like if we subtract the Italy into the Germany and then add the Hitler, and it will lead us to the direction of E is Mussolini. What semantic clusters? Like what I've said in above, over time semantic regions emerge naturally. What does that mean, regions emerge naturally? Because at the first place in the during the training, at the first place, the regions are not are clusters not like this. They are not arranged, but during the training they automatically emerge from each others, because the model learns that this royalty belongs in these regions, these fruits are belong in these regions, and so on and so forth. Examples: hereditary region, king, queen, emperor, prince, throne. Have the throne region. The first region is this. The animal region is here. And nobody manually creates these clusters. They emerge from context statistics automatically during the training. Because their vector values are adjusted, so they naturally automatically form the different regions. And RGB analogy. What's RGB analogy? Is the colors representations that if we combine these three values of colors, they form different color values. Like purple is a combination of the RGB values. Similarly, the word meaning, like king, is combination of embedding dimensions. That's why it becomes the word value king. No single dimension fully defines the meaning. The entire pattern matters. So the massive data sets embedding models require huge data sets like books, articles, websites, conversations, forums, transcripts, discussions. Why? Because the model learns statistical language patterns. And more data provides, the richer the context, stronger concurrent statistics, better generalization, more semantic coverage. Imagine if we have too small amount of data, it could list bias and data that that the model would produce. They can learn that this king, this particular words is often appears in the whole data sets that provide into the model. Next, advice in data. Large datasets improve coverage but do not automatically remove bias. Embeddings learns that's why we should be mindful of the data that we fed into the training, because the model also learn it. If bias associations like this, if bias associations appear frequently, models can learn to them. It appears frequently. So if the bias or lies appears frequently, the model could also learn that. This became the major area of AI ethics research. Next is validation and testing. Embedding systems can be evaluated using context prediction accuracy. Can the model predict nearby words? Similarly, tasks the semantically related words to become nearby. So, like for example, analogy test, king minus man plus woman is equal to queen. Successful analogies indicate meaningful geometric structure. And validation is testing in importance because we could see that if the model actually learn or just memorize. If we have the validation accuracy, that's too well, but during the training it is 100%. I mean, it's doing well also, but in the validation test is too low. It means the model actually memorize it during the learning, and if it's too perfect, it's also learn the noise that it should not be like that. So validation and testings is so important also, like because we actually testing or validating that can the model predict nearby words, like similar text, do semantically correlated words become nearby. Like for example, if you input the word that it's not seen before, or we have input the king, does output the semantically related words. So here's the final mental model. So the embedding model starts from random vectors. It reads huge amount of text, generate context pairs automatically, predict nearby words, and compute loss, and adjust vectors with the gradient descent. Repeat a billion times. Semantic geometry emerges, and they clustered in the embedding space. So meaning is not natural, manually programmed. It emerges from statistical language patterns, prediction optimization, high dimensional geometry, distributed representations. So this is the foundation of modern natural language processing and many modern AI systems.